Good afternoon. So this is Dr. Madhusudana Reddy. This video session for thought bitting first sem EEE students. Second sem, sorry for first sem, second sem EEE students. Subject is design of photovoltaic system. Unit 1, PV solar cell. Already I covered basic introduction part. What is the solar cell and what is the historical property of solar cell and what is the difference between cell and module and what are the different types of solar modules are available already. In this session, I'll continue with equivalent circuit of one diode, two resistor model and characteristics of so these things I will cover in this. See here, this is about the equivalent circuit. So what is this equivalent circuit? Will continue. Before that, I'll start with a small introduction part of what is this solar cell. See here, this is about, for example, it is a PN junction diode, like a, it is applicable like a PN junction diode. Yeah, this is about like a PN junction diode. So whenever see the characteristics of the PN junction diode, VI characteristics, see here. This is about IV, for example. This is about I, and this is about the V. So let me go for it. What you are getting is IV characteristics. You slowly see here, you are obtaining like this. Okay, it's a saturation. It's a saturation. Okay, you can understood that. So this is about the IV characteristics here, and this portion up to this, and this is about the saturation. And it'll come back here. But what about this diode? Diode is always a passive element which receives energy and which consumes energy. But what about this photovoltaic? Mean a solar cell? Solar cell is not a passive element. It is an active element which always supplies energy, which always gives energy. So we connected a photo effect to the diode. When you connect this photo effect to the diode, okay, this photo current will produce, that current will be distributed across. Whenever you go to this resistance is connected always in parallel with diode, and this resistance is connected because it's a practical. As a practical, every practical source should contain the internal resistance. If it is a current source, resistance is connected in parallel. If it is a voltage source, resistance is connected in series. So that's why we are connected resistance in series and resistance in parallel. Why? Because this photovoltaic effect internal, which should contain the internal resistance. Okay, this combined portion is called as a source. Now it acts as a source. Diode will act as a source. So when this diode acts as a source, how these characteristics are modified? So these characteristics are tilted. How these characteristics are tilted, I'll show them. For example, you extended these characteristics. Okay, I'll show that how this is extended. I'll show that. For example, so like this, the characteristics are like this. Okay, it's downward. These characteristics are tilted. Tilted means these characteristics are like this. Okay, these tilted means inverted. The characteristics are inverted. So now what's happened? So This is not individual diode. It is the interconnection of this photovoltaic effect. Now, these characteristics are limited like this. Okay. So this is about the IV characteristics of solar cell. IV characteristics of solar cell. Okay. See here, solar cell or module. So this is about the IV characteristics. See here, in this IV characteristics, this point is this point. For example, you made as a resistance. If R is equal to 0, then what about this I? V by R. Okay, V by 0, then infinity. Current is infinity mean, what about this current is infinity? Voltage is 0. Voltage is 0. So this is the portion here. Okay. So R is equal to 0 like this. For example, R is equal to infinity. Then what about this I? V by R. Okay. V by infinity. And it becomes as a 0. Current is 0. Okay. Current is 0. What cases? Which contain VOC. So VOC. At this case, R is equal to infinity. But at this case, R is equal to 0. You are having a short circuit current, infinity current. Okay. So that is about this. That is about this. Yeah. Okay. See here. So that there are 2 points for obtaining. What are the 2 points? Number 1 is short circuit current. Okay. Number 1 is short circuit current. Number 1 is short circuit current. Number 2 is open circuit voltage. And we'll come back here. You're obtaining another curve is called as a power curve. Okay. When we're having a power curve. So let me take a one maximum. So here, this is about VM, sorry, IM. And this is about IM, this point IM, and this point VM, and this point VM. So this is about the IM. That I will show. See here. So this is about the equivalent circuit of a solar cell which contain actual diode, and we are applying the photocurrent, and which is connected to the actual practical scenario of resistance shunt and as well as series resistance. Shunt resistance is connected in parallel, series resistance connected in series, and this is about the load impedance. Here this is about the equivalent circuit, and you'll come back here symbol. In future, we don't draw this complete structure of the PV cell. Just this complete structure of the PV cell can be redrawn like this. Can be redrawn like this. Okay. This is about the solar PV cell, solar symbol. Okay. And which is connected to anode and cathode. Anode and cathode. So this is about the anode and this is about the cathode. Okay. And you understood that. So this is about equivalence. So we have here, these are all the theory, the symbol of a photovoltaic, the terminal voltage V, terminal current is I, that is supposed to flow out of terminal A and nothing but the anode, and also have seen before the equivalent model of this photovoltaic cell, where the constant current source representing the photocurrent. Photocurrent is basically directly proportional to the incident solar power, how much of power is generating, how much of power is delivering from your solar. So this is primarily resource reset, all other parameters sinks disappear. So we remember actually the diode acts as a sink, but now whenever you apply the photocurrent, that sink becomes as a source. That is about this meaning. And we'll come back here. So IP represents the light generated current in solar cell. ID represents the voltage dependent current. ISH represents the current loss due to shunt resistance. ID is modal. So let me go for it here. You know the formula for ID. This is the diode current already learned in electronic devices, CDs. So I not into exponential of V plus I into RS. How can you say that V plus IRS? Let me go back. So this is about the V now. V plus I into RS. Gives the voltage across resistance RS, which gives the voltage across the diode, which gives the voltage across the photo. Okay, understood? So V plus I into RS. So that's why. So, okay, characteristics of PV cell. First, I'm not explaining. So equivalent circuit model define the entire IV curve. So which gives I is equal to IP minus ID minus ASH. How you are obtaining this? This ID. So sum of entering current should be equal to leaving current. ID plus ISH plus I. Therefore, I is equal to IP minus ID minus ISH. IP minus ID minus ISH. Current ID is nothing but the diode current. ISH is nothing but the current due to the shunt resistance. Okay. Then we need to determine this. What is the ID? I naught is the exponential of V plus I RS divided by N into VT minus 1. Here I naught is nothing but reverse saturation. Okay, RS is the resistance, N is the diode ideality factor, and the VT is the thermal equivalent voltage. Nothing but the forbidden energy gap. You know that what is the forbidden energy gap for silicon? 0.5 volts. When you apply that 0.7 volts, 0.7 volts, immediately the diode will conduct. So that voltage is called as the thermal equivalent voltage or a temperature voltage. Okay, temperature equivalent voltage. Next, we'll come back here. I naught into the exponential of V plus IRS divided by N into V2 minus 1, VT, and I told you, again this has another formula, KT divided by Q. What is the K? Boltzmann constant. And what is this T? Temperature. What is this Q? Charge of an electron is 1.6 into 10 power minus 19 coulombs. When you pick up this N, you substitute this K and T, okay, you'll get into this value K and Q, K and Q. Okay, K is equal to some one or two values you can pick up. Then this VT is modified as T by 11,600. Q is equal to 1.602 into 10 power minus 19 coulombs. When you substitute, you'll get into this solution. Okay, therefore I naught is equal to reverse saturation current. It is also another formula, K into T power M into exponential of minus Vg naught divided by N into Vt. Vg naught is nothing but forbidden energy gap. Forbidden energy gap. Okay. So M is equal to 1.5, for example, silicon. And this is about the exponential of the I current form. I is equal to IP minus I naught into exponential of V plus IRS divided by NV2 minus 1 minus V plus IRS divided by RS. This is about ISH. So I naught is the saturation current. Already I told you reverse saturation. It is the thermal voltage or volt equivalent temperature, which gives us this formula. And Boltzmann constant, we pick up this value 1.381 in 10 power minus 23 joules per Kelvin. And Q we pick up. Based on these two values, we get into the solution of VT is this. Okay. And ISH already I told you this value. By substituting all, we are expressing this value. Okay. There are 5 important parameters are very important. What are those? Light current and diode reverse saturation current, series resistance, shunt resistance, diode ideality. So this is about for a single cell. If you have a more than single cell, you are connecting number of cells in series and like array. Then what about that is called the module or array comprising NSC cells. Already explained you in the earlier case in the earlier video. You identified 12 rows and 6 columns. How many cells? 12, 6, 72. So you pick up this in the place of the cells, 72 cells. So how to modify this equation? This is the I module is equal to I cell. The module is equal to NS into V cell. NS into V cell. Okay. So therefore, the module current equal to IL minus what IL is equal to IP minus I naught into exponential of M plus IM NS. We added NS. Here also we added, where VM and IM are the voltage and current of the module respectively. So, okay, so that is about this. Then we can get into the solution of this A value, okay, for a single variable, NS into N KTLC divided by Q. And you'll see here characteristics, already I told you. So therefore, this is about the VI characteristics. When you pick up this voltage is equal to 0, when possible, R is equal to infinity. Mean this resistance, this load resistance, we can make as a infinity when it is possible. I is 0. Sorry, ISCE, I we can make as a short circuit. When you made as a short circuit, voltage should VOC become as a 0. When this VOC is 0, you substitute this V is equal to 0. V is equal to 0. Okay. Then RS divided by NVT eliminated, V is equal to 0. RS by RSH. RSH is much more resistance. Why? Because a parallel resistance should be more and series resistance should be very, very less. So less divided by more, we can eliminate this value. We can eliminate this value. So therefore, IS is equal to IP. So at this position, we are always obtaining a short circuit current. We are always proportional to the solar power, or also part of the insulation. So we remember the solar cell short circuit current always proportional to the solar power which come from solar, okay, energy. It's proportional to the IP. Okay, this is equal to IP. Okay, next case. So let us have in place of IV gas PV cell. So okay, see here the first point is the intersection here. This here short circuit point. Okay, here what's ISC like this. You put as a V0. Okay, then next we'll come back here. You open circuit. Open circuited mean ISC is equal to 0. ISC is not here. Then in the place of V, you can place the VOC. Okay. In the place of I, you can put the 0. Therefore, VOC divided by NVT. VOC divided by RSH. RSH is much more. We can neglect. So therefore, here I is also 0. Therefore, IP, here you'll go to this. You are getting the solution. IP is equal to I naught into this all. By taking the natural logarithm, all these things, you get into the solution of this. VOC is equal to NVT into natural logarithm of IP plus I naught divided by I naught. Same story we are obtaining here. All these things. Next, if you have increasing this, okay, you are changing the points of short circuit and open circuit voltages. The curves are increasing like this. VOC points. How can it is possible? By changing the resistance. Okay. Next, you'll come back here. Already I explained you. So there are two operating points are there in cell. What are those two operating points? Three operating points. Number one is short circuit current, one of the operating point. Number two, VOC, open circuit voltage, operating point. And number three, peak power operating point. Okay. So these are the three operating points that are available in any solar cell IV that we remember. So already I told you how we are obtaining these IV characteristics. It is a tilted characteristics of diode. Tilted characteristics of diode. Then this is about short circuit and VOC is an ideal case. It's not a practical case. But in case of the practical case, so these two values are obtained. What are those? Maximum current and maximum voltage. At this point, you are obtaining as a maximum power on your PV curve. So this is the PV and this is about the IV curve. Okay. So from PV curve, we can understand this is the maximum power you are obtaining. Okay. So this is the things we are explaining here. Consider IV curve. X-axis has the voltage, Y-axis has current as well as power. Okay, both. And consider, for example, this point as equal to 0. And therefore, we consider as VOC and ISC and PM also. See here, same thing we explain.